Hello, Josie. We'll get started here pretty soon. We'll get started in a couple minutes. If you wanted to go get something to drink or something to eat or the restroom or something, that's fine. I'm not sure who has the number 1011999. I'm going to have to kick you out. I need you to put your name in. Sorry. We'll get started in a minute or so. If you want to go get something to eat, drink, something like that, feel free to do that. Okay, I think we're going to go ahead and get started. So I hope you guys are all doing okay. Hopefully nobody you know has gotten sick or anything, and everybody's safe. Um, so I'm sure you've heard some of the exciting news with what's going on with AP. So I thought maybe I'd share what I know up to this point. Let me go ahead and share my desktop with you. All right. So so I'm pretty sure you probably know this already, that the last day for AP classes is actually the day of the test. So that's kind of exciting. So that's kind of a nice surprise. For us, the test is May the 11th, which is actually the very first day of AP testing. It's a Monday. And so since that's actually the day of the test, and I don't like to help students start panicking on the day of the test, we're not going to do any review on that day or anything. So in other words, there's not going to be a really class on that day either. So really the last day for us is going to be May the 8th, which is a Friday. And so after that, we're done. Let me let you know a little bit of what I know about the test. It might have changed, and I'm sure you probably know about this too. It's going to be 45 minutes. It's going to be on the computer. Um, and it's going to be free response. My understanding is it's open notes and stuff like that, but understand it's timed. So it's not like you're going to be able to chat with your best friend probably and get some help on it or anything like that. So I wouldn't worry about that kind of stuff. Just go in there and do the best you can on it. I think there's two questions if I remember correctly, that are a free response. I think one of them, if I remember correctly, is like 15 points or minutes or something. I can't remember exactly. And the other one I think is 10 or 12. I'll look that up again. I have no fear about getting through all the unit we're in right now, momentum. It's a pretty simple unit. I think we're gonna get done with it pretty easily. I am a little bit worried about getting through the rotational dynamics unit. However, I will let you know this. The very first year we started doing this class, AP Physics Mechanics, well, maybe I should tell you before this class, it was actually honors physics. It's kind of like, you know, how there's honors chemistry. And I'd always been kind of thinking about how the fact in honors physics, we covered pretty much everything that was on the AP mechanics test, except for the rotational dynamics. And so I always thought, well, you know, there's some really awesome students in here that were, you know, gifted and talented students, alpha students. And I'm thinking I kind of felt like I was cheating them out of the possibility of maybe taking the AP test. I know some of them would buckle down and actually study on their own. And so students were kind of encouraging me to do that. So that's why we kind of started in AP Physics. That first year, we didn't even get to the rotational dynamics. So the thing that I'm worried about this year. In fact, I didn't even tell them going into the test, hey, there's one more unit we haven't covered, because I didn't want to panic them on the test or anything. I had one student, though, I actually had more than one student, but I said, you know, you ought to study this stuff on your own too, outside of class. Of course they did. And there was one student who really did a lot of studying on her own, and she got a 5 on the exam. Um, and so that's what I'm kind of encouraging you. If you're one of those people that you have to get a 5, I think you can get a 5, especially now that you know this is the section you need to work on. That rotational dynamics section. Had lots of students that got 3s and 4s though. So, I mean, I think you can do it. So anyway, so again, the last day of class is going to be for us, it's going to be Friday, May the 8th. Right. Do you have any questions on that? I've also opened up the AP Classroom so you can do some practice questions on there. I think I shared with you that link for the online classes that they're offering. You would have to watch the video recording of it because I think it's actually kind of like right now or something that's going on. I don't know that I'd look at all the review stuff. I think we could do a pretty good job in here of reviewing with the internet homework. Oh, I probably should mention that. Internet homework's due this Sunday. Don't forget, you only have to get 6 of them, um, not all 14. Um, so I don't know that I worry about those review. I think what I'd look at is the stuff we haven't covered, which will be the rotational dynamics. That's it. All right, so
I have
today,
a, sorry.
oh, sorry,
I
question?
have a question. I know that some of the like AP classes, they're like cutting a couple of units off the end of it.
Yep.
Are they doing that for physics?
Yes, they are, but the problem was I don't do the, I don't, in fact, I'm sure it's true for your other, for the other AP classes, maybe. I didn't do them in the order that
Mhm.
they say. And so the 2 units they're cutting out are the 2 units we've done already. For,
Oh,
yeah, they're cutting out uniform circular motion, universal gravity, which we just took a test on. That was the one that was online.
okay.
And also they're cutting out oscillations, like with a pendulum or spring, and we've already looked at that. So that's where you have
Okay.
the t squared equals 4 pi squared something, you know. So
Mhm.
um, so
Yeah, that's fine. I was just wondering.
yeah, the last 2 units that could possibly be on your test would be what they consider, I think, unit 4 and 5. Unit 4 is this momentum, and unit 5 is the rotational dynamics. Again, I'm not worried about getting rotational momentum done. It's just the rotational dynamics. So,
Okay. Thank you.
yep. Um, any other questions? Okay. Um, today, we are going to be whiteboarding we're going to look at your mathematical and graphical models for the explosion lab and for the impulse lab. So I'm trying to make this as much as like we're in the classroom as possible. So I noticed that some people, when I shared this link, I noticed that some people were trying to answer some of the questions on there. I don't expect that of you. It's kind of like in class. I wouldn't expect you to be able to answer the questions on the response sheet, right? You can't do that until after we figure out what the mathematical models are. All I want to know is what are your graphical models? What are your mathematical models? And then from there, then we'll start whiteboarding together the other problems. So um, Oh, also on top of that, I have to somehow be able to grade your participation and kind of see that you're involved. And so there's two ways to do that. You can make your own whiteboard, and that would be fine, and share that with me. Or another way, there's some groups that did this. They collaborated on one whiteboard, but I need to see that everybody, when I go to the history, I need to see that everybody's contributing to the making of the graph, whether it's the axes and the titles and the point protectors and the slope indicators and the actual sketch of the graph, or maybe the mathematical models. It's not that one person has to do everything, but I need somehow, in order, I have to figure out where these participation points are going. So I had groups that would actually contribute on one whiteboard, and that's fine, but I have to see that everybody's involved, right? So anyway, um, if you remember with the explosion lab, what you had is you had these two cars, and they're triggered somehow, and they kind of move away from one another, depending upon how much mass they have, how much inertia. Since they're moving away from one another, one's going to be moving in kind of the positive direction, one's moving in a negative direction, kind of based upon whatever you feel. Okay. All right. So let me check my email real quick. Okay. So we're going to look at the graphical mathematical models that people got for that lab. So let me pull those up here. All right. So I don't remember exactly whose these were, but I'm just going to go through all of them, just kind of like with the whiteboard in class. So it kind of looks like we have an inverse. I will say this, that really, since they're going in opposite directions, they're kind of going apart from one another. This inverse, really, when you graphed it, the ratio of the velocities, one of them has to be negative. That means the ratio of the velocity has to be a negative. So I don't think it'll look like this. I think it will actually look upside down like this. Whoops, sorry. And so to make this graph correct, you can either invert or rotate the coordinate system, or probably an easier way is just kind of draw another axis up here. So something like that, okay? Which means I think when you linearize this, then I think instead of being upward like this, I think what happens is it kind of goes down like this. Okay, so you might be thinking, why didn't you, Mr. Limfesti, why didn't you go ahead and make the axes kind of rotated around? Well, I didn't want to give you too much of a hint of what the graph would look like, because one of the things that students trip up on in this section is this new thing we're looking at, is it scalar or is it a vector quantity? And we'll talk more about that in a second, but let's look at some other graphs. So again, a kind of an inverse, but I think it's really upside down. Looks like an inverse. Notice this one's kind of upside down. And I think this linearized graph then would also go the other direction, okay? Looks like an inverse. Okay, an inverse, it's the bottom one down here. Inverse. Again, I think it's going to be kind of an inverse upside down. Wow, that person worked really hard. Inverse, again, I think all you have to do then for this one is just simply draw an axis up here. Don't forget to label your axes and stuff when we eventually turn this in as a lab. Kind of an inverse thing. Now it would be upside down, of course. Looks like inverse, again, upside down, inverse, inverse. Okay, so it looks to me like everybody agreed that it was inverse. And so then when you're looking at, let's see, I think we'll go to this one. So then when we're looking at the mathematical model, so if you look at this, they say the velocity of the red compared to the velocity of the blue would be equal to -1 times the, now it's going to be the inverse of the ratio. So notice over here it's red to blue, and now it becomes blue to red because you had to invert it. So let's see it. Yeah, we didn't really, some people didn't really spell that out. Okay. Okay. Some people did and some people didn't. I do notice that the coefficient for most of the groups looks like it's -1. So this one here, they have 1, but I think it'd really be -1. That's -1. This group here had 0.023. Oh, wait a second. They said it was a top opening model. I see. Okay, so that's really going to be an inverse. So that's probably what messed them up there, probably. The coefficient looks like 1, but it actually would be a -1. Again, the coefficient's 1, should be a -1. So -1. Again, that would be a -1, -1, -1, -1. Again, that should be -1 there. Should be a -1. Okay, so -1, I think most of us have something like that, -1. All right, I'm going to kind of work on this whiteboard a little bit. I really don't like this idea of trying to memorize this new relationship as being a fraction. So what I want to do is I want to multiply both sides by velocity of the blue and multiply both sides by the mass of the red to get rid of the fractions. And so when I do that, I would end up getting velocity of the red times the mass of the red equals -1 times the mass of the blue times the velocity of blue, except I'm going to have the same order as I have on the left, so I'm going to make it velocity of the blue times the mass of the blue. So that really is the same statement as we have up here, but now I don't have to worry about it being a fraction. So at this point, I need to give you a new definition, and that definition is for momentum. So momentum is defined as the product of mass and velocity. In other words, it's kind of like inertia in motion. So when you're thinking about those particles that were kind of exploding away from one another, the one that was more massive, had more inertia, wasn't moving quite as fast as the other one was. So it's related to the inertia. It's kind of like inertia in motion. Okay, now the equation. The new symbol that we're going to use for momentum is a P. I used to know the reason for it. I think the historical reason is, if I remember correctly, Newton was one of the first people to kind of come up with this quantity. He knows this relationship first. And I think that he used the Latin word for progress. I don't remember exactly what the Latin word for progress was. It was something close to progress. And so he used the P for momentum, the progress of this object moving, is equal to mass times velocity. Since velocity is a vector quantity, so is momentum. So I'm going to try to put vector notation here. So I'm going to put this over the velocity. I'm going to put one over the momentum as well. So momentum is a vector quantity. Okay. Any questions there? So the graphical relationship is, we all said it was kind of an inverse relationship, actually kind of a negative inverse relationship. And so we're seeing that the product of both objects' momentum is similar. Now, notice how there's this negative symbol. So in other words, when this thing is exploding away, the momentum of this one is equal to the negative of momentum of this one. Is that the initial momentum or final momentum? Or maybe I should say it a different way. What was the momentum before the explosion, when it was just sitting there? What was the momentum of either one of them?
0.
It was 0, yeah. And so really this is the final momentum. This is after it explodes away. So I'm going to put an F here. This is really the final momentum. Okay. I think that's all I want to do for that lab. Okay. Any questions on that? Okay. All right. So let me just minimize that, I guess. And the next one we're going to look at is the impulse. So again, I don't remember who, I'm just going to go through all these. So this group found, actually, I probably should talk about impulse a little bit before we get into this, because I had to give you a definition. Impulse, I defined as being equal to the area of a force time graph. So I'm going to expand on that a little bit. If you remember back for energy, we were looking at a spring, let's say, and so we plotted the spring force, F spring, versus the displacement, X, and the graph kind of looked like this. And we defined the area. Let's see if I can do this. Oops, nope, that didn't work. We defined the area of this as energy. So this area of this thing was called energy. Well, this is not the same thing as impulse, because impulse is really force time graph. This is force displacement graph. So I'm going to change this. Let's say now we have a force time graph. And let's say that maybe you're looking at punching a pillow. So imagine you're just getting tired, that's pandemic, you're claustrophobic, you need to get out, so you're punching a pillow. I don't know why. So you're punching a pillow. If you're thinking about it, when you first touch the pillow, the force is going to start to increase. And then at some point, the force is going to be some maximum. And then once you get full extension, it's going to start getting smaller again. In other words, the graph would look something like this. Maybe, okay? The area of this graph, that's called not the energy, because this is force time. Oh, by the way, it doesn't have to be a spring. It can be any force. The area of this graph is called the impulse. And so if I wanted to find the impulse, I just find the area of this, okay? In the particular lab you were looking at, I think it was an astronaut, and they had like a jetpack or something. And so when they applied this force was a constant force. So it didn't look like this. Your graph would have looked more like this. And so you had some constant force. Still, the area is called the impulse, but you had some constant force being exerted over a certain amount of time. And then the astronaut moved between two markers, and so you're able to figure out the velocity. And so what you plotted was the impulse versus the, excuse me, wait a second. Wait a second, are we saying that the impulse, I don't think that's right, is it? Because, so force and time, weren't those things that you could change, force and time? So I think those were probably the dependent variables. So I think I'm going to switch this around. I think the impulse really is, in this case, I think the impulse is the deep or independent variable. I think the change in momentum, if I could do this, sorry, I think the change in momentum is actually the dependent variable. In other words, by having the force be bigger or the time be bigger, then it had a greater change in velocity. I think the velocity is probably the dependent one. Are we okay with that? Yeah, okay. I mean, the graph still looks the same, right? So anyway, so in your particular situation, I think the impulse graph kind of would have looked like this. So anyway, this group right here had kind of a, it looks like a direct relationship. This group here also had kind of a direct relationship, 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 direct relationship. Okay. So actually this group, I guess, got a linear relationship. They had a y-intercept. Okay, so I think I want to go back. See, they had direct, they had direct, they had direct, 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 direct. So I think maybe this group, maybe check to see if you could drop off the y-intercept. This group had a slope of about 0.859. Looks like this group had a slope of 1. Slope of 1. Slope of 1. Looks like slope of 1. Didn't get an equation. Slope of 1. Didn't get an equation. Slope of 1. Whoa. Slope of 6.7. Okay. Slope of 0.79. 0.978. It looks to me like the consensus is it's about 1. Okay, so let's see if I can just pick one here. How about we come to this one? So first of all, I'm going to change your equation a little bit. This is really going to be mass times velocity. Okay, and over here for the impulse, the way you found the impulse was you did force times time. You could also use the symbol J. J is the symbol that we sometimes use for impulse as well. So force times, the reason why you could do force times time here is because it was kind of a square looking graph, a rectangle, okay? By the way, for this mass times velocity, was that the initial velocity? Was that the final velocity? If somebody could shout it out. I have to turn on your microphone or your stop, unmute yourself. Was that the initial velocity or final velocity of the astronaut?
That'd be the final velocity.
Yeah, that's the final velocity. Yep. So I'm going to put VF here. In fact, what was the initial velocity?
0.
0, right. Okay, so it looks to me like we have the following statement. We have something like this. We're saying the impulse equals, well, it's not equaling momentum. It's not equaling final momentum either. It's actually equaling change in momentum. Change in momentum. The reason why is because the initial momentum was equal to 0. If the astronaut was already moving, let's say started out with the speed of not 0, but let's say 10 or something like that, you wouldn't have gotten an equation like this. We would have actually had a y-intercept, like the group over here got a y-intercept. I don't think, could you have the person moving at first? No, I can't remember. But anyway, so maybe that would explain it. So anyway, impulses equals change in momentum. So I'm going to see if I can use symbols to represent this. Okay, so impulse, sometimes we use the letter J for impulse, equals change in momentum. Well, that would be like delta P. So let's see if I can draw a triangle here. All right, and let's see if, now since momentum's a vector, that means impulse is also a vector. Oops. So that would be the mathematical model that we're finding, that the impulse is equal to a change in momentum. Now, when it's a really simple graph, like this one here, we could actually just simply write the following relationship then. We could say that force times t, force times time, is equal to mvf minus mvi, where mvf would be the final momentum and mvi would be the initial momentum. Now realize this equation with the ft in it, that's only true when your impulse graph looks like this. If your impulse graph would look like this, it wouldn't be force times time. It would be like 1/2 of force times time, right? Because the area of a triangle is 1/2 the base times the height. Or let's say your impulse graph looks like, see if I can do this. Probably can't. Oh, flatten that curve. Been cooped up too long. Let's say we have something that looks like that. You would actually have to integrate this. So it's kind of getting into a calculus a little bit. And so that's why I'm just going to leave it as usually a J over here. A J equals change in momentum. But if it's simple like your lab was, then F times T equals MVF minus MVI. So a couple things I want to reiterate here is that impulse is a vector quantity, just like momentum is a vector quantity. Also, I want you to understand that impulse does not equal final momentum. Impulse does not equal initial momentum. Impulse equals change in momentum. In other words, impulses cause changes in momentum. I don't know if anybody's into sports, golf, anything like that. You always hear your coach telling you to do follow through. Make sure you follow through. Let's say basketball, follow through, or even golf, follow through. The reason why is you're applying that force for a greater length of time, which will cause the change of momentum to be more. And usually that's a good thing. You want to go further or whatever. Any questions? Okay, so I think that's kind of all. Don't leave yet because I want to kind of take attendance here in a second, but I think that's kind of all we're going to do today. I know you're thinking, well, we didn't get through the rest of the lab. That's all right. That doesn't mean you need to do it on your own. Absolutely not. We're going to whiteboard it together. That'll be on Monday. Yeah, Monday. So if you want to work ahead, fine. You don't need to though. These labs are only going to be due after we get done whiteboarding the whole thing. So let me kind of close this out. Okay, and so stick around here for a second. Close this out. Okay, so what you still need to do then is you need to take this attendance quiz thing. Really, this attendance quiz is just going to be over the stuff we've done. So just a graphical and mathematical models. It should be super easy. But you need to have the code. So I need to give you that code. And that code is right here. So it shouldn't take you very long, 15 minutes. So there's the code. Make sure you record that. I need to go back. I just want to make sure I clicked on the right thing. See, I'm getting all mixed up. Yeah, that's right. I did right. Okay, sorry. So that's kind of what you would be doing for today. So stick around here. I need to stop sharing. All right, so I need to take attendance, and I think the easiest way is just to take a snipping. I have all your lovely faces and names in here. Perfect. Okay, let me minimize that. All right, any questions? Okay, well, that's it. Don't forget about internet homework, and stay safe out there. All right, okay, bye.
Bye.
See ya.